Here we define a very useful function called the integral function, which f of x, or um, in which big F of x is equal to the integral from a to x of f of t dt. And this is an incredibly useful function and shows up all the time in applications. For example, if f is, say, velocity of an object, then we saw from the last section that the integral from a to x will give us the total distance that the object traveled. So f of x equaling the integral from a to x f of t dt would give us how far the object traveled between time points a to x, right? So whatever x is, we could put it in there. So if we wanted to know how far the object traveled in, an interval of 7 long, like so this would be f of a plus 7, right? This would tell us this is the distance traveled by the object. So this is a very handy function, and what the theorem here says is that this function is continuous. So again, the textbook goes through a very nice proof using our ideas that let's kind of sketch it out, and we'll have a picture. So let's say I don't know, C is infinitely close to D, then we want to show then that f of C would also be infinitely close to f of D. If you recall, that's one of our definitions of continuity. Whenever two values are infinitely close to each other, their output of the function will also be infinitely close. So we want to prove that that's true. And again, I don't want to go down into standard parts. It's done very well in the textbook, but I'm going to take a look at the graph of some general function and show ourselves that this should still be true. So again, we've got our arbitrary function y equals f of x. And if we, so again, we're looking at the integral. So f of c is the integral from of a to, say, c. And if so if we looked at the area of that region, it would look something like this. And so the value of c is here. And if we, so we want to say that the integral from f of c to f of d, so c and d are infinitely close, so they're right in here. And if it's equal, then all we have to show is that this little infinitesimal, or this little region strip here, is an infinitesimal area, and so they're infinitely close. So let's get our magnifying glass out and zooming into the x-axis would look something like this, where this distance here between C and D is infinitesimally small, right? Because C and D are infinitely close to each other. So the width here is an infinitesimal. And now if we zoomed up to the height of this rectangle, so we know the base is infinitesimally small. And we look at the height of this rectangle, so zooming in there, we see again that this difference in height is also an infinitesimal, because why should that be? Well, because f is continuous. And so f of c is infinitesimally close to f of d. So this green region here would be the integral from c to d of f of x dx. And since it's an infinitely small base and the difference between them are infinitely small, then this itself would also be an infinitesimal, right? And why is that important? Well, now coming back to what is f of c, big F of c and big F of d, well, big F of C is the integral from a to c of f of x dx. F of d is the integral from a to d f of x dx. And so then if I look at their difference, f of c minus f of d, well, it's equal to the integral from a to c f of x dx minus the integral from a to d f of x dx. But then we can flip this order of integration, and that negative sign would turn into a positive. So giving myself some room, this would be equal to the integral from a to c f of x dx plus the integral from d to a f of x dx. And now we are in the position of the additive property because my lower bound here, a, is the same as my upper bound there. And so then this, by the additive property, is equal to the integral from, say, d to c of f of x dx, which we said is an infinitesimal. But if this is an infinitesimal, then that means f of c is infinitely close to f of d, telling us that this function is continuous. Okay, that's great. It's continuous. Well, where does that get us? Well, it helps us here in a second in our fundamental theorem of calculus. But before we state the fundamental theorem, I need to define one more object. And let me clean the blackboard and post that up. So if little f and big F are functions, and it just so happens that f prime of x, so the derivative of big F, is equal to little f, we would say that big F is an antiderivative of f of x. So let me give an example of what I mean here. If, say, f of x is x squared, and big F of x is equal to, say, 1/3 x cubed plus 7. Then notice that f prime, the derivative of big F, is equal to, well, this is the power rule, so the 3 comes down, and it's going to cancel with this 3. So it's equal to x squared plus the derivative of 7, which is 0. So this is equal to f of x. And so big F is an antiderivative of little f. Another example, if let's say f of x is equal to cosine of x, and big F of x is equal to sine of x, well then the derivative of sine is cosine. F prime of x is cosine of x, which is our little f of x. And so big F of x is an antiderivative of little f. All right, so we need antiderivatives to define in our definition of the fundamental theorem of calculus, which I will now post up here. And as I promised, this will give us a nice, quick, and easy means of computing definite integrals. So the fundamental theorem of calculus has two parts. We always have to start with f being continuous. That way we can actually have an integral. And then the first part says that if or says that the integral function, f of x, defined as the integral from a to x, f of t dt, is an antiderivative of f. In other words, if I take the differential of this, I would just get left behind f of x dx. Now, something that's really key, this t in the integral is changed into an x right here because we're taking the derivative with respect to x. And so students oftentimes think that this theorem is way too easy, that if I've got an integral function, the derivative is just a matter of erasing the integral sign and replacing t's with x. That's all that's going on here. So that's the first part of the fundamental theorem of calculus. The second part, which is what most students remember, is that if I want to integrate f of x dx between a and b, then I just need to find any antiderivative, and evaluate it at its endpoints. So, and this is notation I will use throughout, that if I have f of x with a bar and then ab to it, I'm saying put b into the function and then put a into the function and compute their difference. And so the second part of the fundamental theorem of calculus says, look, if I've got any antiderivative, f, then the integral is simply equal to the difference of f of b minus f of a. Now, I will actually prove the fundamental theorem in the last video, but this second part maybe is not too terribly surprising. Again, if you recall back from the previous section, if we think of f as a rate of change, then big F is my position function, right? The antiderivative is just my position function. Well, then, if the integral computes how far the particle or object has traveled, then it's just going to be its terminal position minus its initial position. Right? That's how we would calculate displacement, or that's how we calculate total distance. We figure out where it is when it ends. We know where it was when it began, and the difference between that is the total distance. So the second part should fit in with your intuition, but what it says more importantly, and this will continue on through your studies in calculus, that if I want to evaluate a definite integral, I've got to first find an antiderivative, and then I just evaluate that antiderivative between its bounds and take its difference. So for example, let's say I want to know what is the integral between 0 and 3 of x squared with respect to dx. Well, we know that if f of x is equal to 1/3 x cubed, then f prime is equal to x squared. So 1/3 x cubed is an antiderivative. And so this integral is simply equal to 1/3 x cubed evaluated between 0 and 3, which is equal to 1/3 3 cubed minus 1/3 0 cubed, which is equal to 9. One more example for this video, we'll look at, let's say that c is a constant. Right? And I want to know what is the integral between a and b of c with respect to x. So c is a constant. Well, if c is a constant, then f of x equaling cx is an antiderivative, since f prime of x is just c. So since cx is an antiderivative of c, then by the fundamental theorem, this is equal to cx evaluated between a and b, which is equal to c times b minus A. Now, this we could have figured out even without the fundamental theorem, since if C is a constant, and if I kind of graphed what this function looks like, so here's A, here's B, and C's up here, then our function constant, the area under it, is just a rectangle, right? That area is just a rectangle with length B minus A and height C, so its area would be C times B minus A, which we know. But the fundamental theorem of calculus confirms that as well. So in the next video, I'll work out a few more exercises, and then we'll finally prove the fundamental theorem of calculus.